Good evening.
Good evening. Good evening.
Yeah.
I see you have already started.
Yeah, I just thought I should. I knew you were in the other session, I think. So I
No,
just thought
yeah.
I should keep it on for the attendees to come in and feel welcome.
Sure. Thanks.
Okay. I also noticed that Shashi Ranjan has also not joined. Could you call him and ask him to join?
Yeah. Yeah, I'll do that. I had spoken with him in the morning when I had told him that he has to do this twice today at 11:30 and also at 5 o'clock.
Okay.
So he knows. Let me just poke him once.
Sure.
So almost the final 1 hour, right, Raj?
Yes.
Yeah.
Thank you so much. And I'm
Thank
sorry.
you.
You were the only one I was bothering in the initial days, and
No, come on. I
otherwise,
say, don't say sorry. I mean, please don't say sorry. Yeah.
okay.
My request. Yeah.
Okay.
So Raj, I've already informed Shashi. Uh, let's see.
Yeah. Thank you.
Yeah. Good evening, Professor Narasimhan.
Good evening.
Professor Narasimhan, it's already 5 o'clock, so you can start whenever say you are ready.
So, good evening, everyone. I think end of the day, but this is also the last of the series of lectures we had planned in the workshop. And you can look at it as the pièce de résistance, or you can look at the final nail in the coffin that we are putting with respect to EID, errors in variables identification. So far we have seen how to identify dynamic models only for CISO systems. Now, how do we extend it for MIMO system, multi-input, multi-output? Okay, and we are going to use the subspace model representation for various reasons and identify it. So let me state the problem here. Essentially, here we are interested in identifying a discrete state space model of a multi-input, multi-output system. It is linear, time invariant, dynamical system, and we are given noisy inputs and outputs. So this is the errors in variables case, where the inputs and outputs are measured with noise, whereas the classical thing assumes inputs are noise-free, known exactly, and people have developed subspace-based methods for identifying what's called the state space model. Okay, so for the classical case, yes, there are approaches available, but even those can be improved, I believe. Or the approach that we are giving, I think, slightly has some advantages over the existing approaches, and especially with respect to order determination as well as the error variance estimation. These two properties are very useful, and they can help even in the classical identification case. But here I'm going to deal with the EID case, and one may ask, why do we actually use a state space representation? Why not use an input-output form? Why don't we break up the problem into, see, input-output model for each pair of input and output, right? So that will actually be identifying multiple CISO models. For every pair of input and output, you try to identify the transfer function or the what we call the discrete representation model. But that itself has a lot of problems. One, by decomposing, you do lose information. What I mean by that is, you don't see the system together, and there is some redundancy you might lose, and therefore the estimation procedure itself can be problematic. Second, there are multiple orders. Now you are estimating an order for each one separately. When you put together the whole thing, it may not be the minimal representation, right? I mean, your system representation may not be minimal, and that's always very useful. For example, in this particular representation also, what we are asking is the number of state variables should be as minimal as possible. What is required for describing the system, not more, not less, right? And if you identify what is called multiple CISO models and try to put it together, you have to do some further reduction and so on. A lot of effort, additional effort has to go into coming up with a minimal realization. So to avoid all of this, we directly go with state space realization, with which looks at the whole problem. It of course complicates it a little bit, but we'll see that, by and large, we can exploit whatever methodology we have developed for the CISO system very nicely for solving this problem also. Okay, so this is going to combine concepts from subspace-based identification that has been used for classical model identification and DIPCA. So it basically combines these two ideas in order to arrive at these estimates for A, B, C, D, and so on. So here I have put a general representation which also contains process noise. So the first equation, forgive me for not using bold letters, which I use for all matrices and vectors, but because I didn't have much time to kind of modify the slides, so I left it as it is. So you take it that these are all multivariate, these are all vectors. X is a state vector, and at time k plus 1, it's related to the state at time k through this transition matrix A, and then it's also related to the true inputs by the matrix B. And there is also uncertainty associated with this model that is described by G times Pk. Pk is the noise vector, and G is the matrix that relates the noise to the states. So those are all independent, you might say, disturbance variables or errors that drives the system, right? Other than the inputs, known inputs. Then we have measurements. the true measurements are first represented. Like I said, for the AV case, we distinguish between the truth and the measured values. So here we have written the true outputs, which are function of the true inputs and the states. You may call it the true states, but here we are not, since states are not measured, we are not putting a star on X's. So these are what we call the true states. And then we have measurements corresponding to the outputs and measurements corresponding to inputs, which are corrupted by noise V and W. Okay. And of course, I mean, I'm sorry again, some notation conflict might be there from earlier slides. W was used as a process noise and V was used as a, I'm sorry, EU and EY was used as measurement noises. But here we have changed the notation again. So bear with me that there's no consistency across lectures. We'll correct it at some point in time. So the most of the talk here, I'm not going to stress so much on dealing with the process noise case, because that's only a slight additional complication. We'll first solve the case when there's only measurement noise without process noise, and then I'll tell you how the extension can be done for the process noise case. So the aim is, given measurements yk and uk, k equals 1 to n, number of measurements capital N, we want to estimate A, B, C, D, and the noise covariance matrices for y and for u, and perhaps if there's process noise, also it's noise covariance matrix. That's the overall problem statement, and that's the dimensionality of all these are indicated here. L is the number of inputs, M is the number of outputs, small n is the number of state variables, and that's it. I mean, the system matrix A, B, C, D, G are all appropriate dimensions. Okay, so that's basically, so M is the number of outputs and L. So total number of inputs plus outputs is M plus L. Okay, so that's the thing, and N is the system order, which is what we don't know. Before we talked about process order for a single input, single output system. Now I'm going to talk about system order, because this is overall representation of all the inputs and outputs together. And so we are going to call this a system order, and we are trying to also, we don't know anything about it, we have to estimate. So the linear, so we look at the special case of no process noise. So in this case, the usual assumptions are made on WK and VK, which is the noise corrupting the input or output measurements. They are independent Gaussian white noise sequences, and we'll call the covariance matrix of errors in y and u as sigma y and sigma u. Maybe I should have used sigma v and sigma w, but for whatever reason, that again the symbols are slightly different. And the P also may have a covariance matrix. Since it's absent, we are just basically ignoring it for the time being, and we are only interested in estimating the system matrices along with the covariance matrix for the errors in y and errors in u. Okay. Order of the system is not known. That also has to be estimated. N. So that's what is stated here. Given all measurements of y and u, order of the system, the covariance matrices, and the ABCD. So very similar if you look at it for the CISO case. There also the model parameters are A and B, small a, small b, the sigma squared y and sigma squared EU and sigma squared EY. And instead of system order, you have process order. Okay. So this is just an extension. You might look at it that way. Okay. So just to recap what we have done. So this also gives you a whole thing of the entire workshop, where we started and where we are going. So notice that the approach we are taking is also a building block approach. So we start with the bottom layer, which we call it PCA looks at you have the core technique, which is PCA, but since it has some limitations, we actually extended it using IPCA. That formed the bedrock for the DIPCA, which does CISO systems. But now we are going to combine with this idea of subspace identification to build the technique for multi-MIMO systems. So it's all built, one is built on top of the other. So we will leverage all the advantages that the earlier techniques actually has to offer. So I'm just here recapping what we have so far seen in the lectures since day one. So we know that we can identify a constraint model given a set of input-output measurements by stacking them, right? We don't distinguish between the variables. We just call them Z star. And if there is a constraint matrix that relates Z star, in the static case, we said given a set of samples of Z, k equals 1 to 1, which may not have a time implication, that we still can extract A by using PCA. But since PCA assumes all the error variances in all the variables Z are identical, so it's not optimal for the heteroscedastic case. So for heteroscedastic case, we actually developed IPCA, which estimates the error covariance matrix, error variances of all these Z variables. Let's say there are, earlier we said there are M such variables. So for all the M variables, we corresponding sigma squared or the variances, error variances are estimated. And that is put together in this diagonal error covariance matrix, sigma E. We use it to scale the data and then apply PCA on the scale data to get the constraint matrix. So IPCA iterates between these two steps. It estimates sigma E given A and estimates A given sigma E by scaling. And hopefully the algorithm will converge, and we know that it converges because we have proof for it, and we will be able to get an estimate of A. Notice also that A that we get is only a basis. That means any linear combination of the rows of A also we might get as a solution. Secondly, we also get the order or the number of constraints in this case by just looking at the number of unity eigenvalues. If the by just seeing how at the number of unity eigenvalues that are present in our what we call scale data matrix or covariance matrix of the scale data, then we can actually identify the number of constraints. So this also requires an outer loop iteration because we don't know D initially. So we start with the large value of D and gradually reduce it, apply a hypothesis testing to check whether there are as many unity eigenvalues as the number of constraints we have guessed. When the hypothesis test says yes, I mean no, we keep decrementing it until we actually find that the hypothesis test actually okays the number of constraints we have guessed. Okay. So once we have done that, we have basically stopped. We have got the number of constraints. We have got the covariance matrix. I'm sorry, error variances as well as the constraint matrix. That's what IPCA does. Now, in order to apply this for a dynamical system, so we looked at the CISO dynamical system represented in this form where eta is the order of the system. Again, we leverage the recast it as a constraint problem, constraint matrix estimation problem by defining what we call the lagged vector. So the lag vector at any time instant k consists of the outputs at time k and all the okay, this should be k minus l up to past l what I call measurements or variables, and then similarly use uk starting at uk up to k minus l. So there are 2l plus 2 variables here in the stacked vector. If you choose a lag of l, you will have 2l plus 2 variables in the stacked vector, and you can construct the measurement corresponding to each of these stacked vector. Right? You can do replace the stars with the measured values. You got the measured value corresponding z star k. Now we know that this equation here, the difference equation, can be represented again in this form, constraint form, and the aim is to actually apply IPCA to get the constraint matrix, or in this case just one row. Okay. And also the error variances associated with the variables in Z. But the variables in Z are only 2, Y and U, and therefore we have to estimate only 2 variances and not many. So we did talk about the identifiability problem and so on and so forth, but we can choose a sufficiently large L, and always the problem will be identifiable in the case. And once we estimate sigma, and from the number of constraints, we can also estimate the order of the system, because there's a relationship between the order and the number of constraints, and L, the lag we choose. So L we know, D is what we get from the unity eigenvalues. IPCA will tell me that. Immediately I get eta. Once we get eta, we can restack the Z with exactly eta. Therefore, there will be only one constraint, and that constraint will give me the parameters of the model. So we run one more what I call scaled PCA on the or what we call the last principal component analysis we do on the scale data, because the sigma E is known by this time, eta is known, so we can stack appropriately, scale it, apply PCA on the scale data, take the last constraint, and obtain all the parameters from there. So that's in summary, how DIPCA actually operates. So DIPCA also gives the model parameters and the error variances, and also estimates the system order using a theoretical criterion. Okay, unlike other methods which try to use some heuristic methods for finding the system order. So that in summary is what we have seen so far. We are going to leverage this again, as I said, for the multivariate case. So this is just again summarizing dynamic IPCA. So we say we start with the lag, fixed a lag L, which is sufficiently large, larger than definitely the system order. Then we make a guess of the number of constraints. Notice there are 2L plus 1 variables. So one less than the number of variables. That many constraints we assume. So among the 2L plus 1, 2L plus 2 variables, we assume 2L plus 1 constraints, literally. Okay, that's the highest number of constraints we can possibly get. We start with that large value, construct the lag matrix for this L, estimate sigma E by applying IPCA, and then we check whether the number of unity eigenvalues you get is equal to D hat. If it is not true, decrement D hat by 1 and repeat. Okay, not decrement eta is wrong, decrement D hat by 1 and repeat until the number of unity eigenvalues of the scaled matrix is equal to D hat. Then you stop. At that point, you've got eta hat from this estimate of D. And now you can reconfigure your data matrix with that appropriate order. We can scale it with sigma E because sigma E has been estimated in this step, in the step number 3. And now we can apply P is the algorithm for Dicta. Okay, we'll see that with small changes we can actually solve the multivariate problem also. Okay, but first the main job is to take the state space form and represent it as a constraint matrix. That's the key, and that has already been done in subspace identification to some extent. Though they don't, not all of them actually call that a constraint matrix, but essentially, if you follow the procedure that is available in subspace identification methods, you can come up with this, what we call the constraint representation of the problem. Once you have done that, we can apply Dicta. That's the whole idea. But still, you'll see you can't directly get the system matrices. You'll have to do further things in order to finally extract. But all that hard work has already been done in subspace-based ID. So we can completely leverage the toolbox that's available there. Fine. So in this particular case, again, we are going to use a lag L, but I'm going to define one more variable called F, which is L plus 1, because L plus 1 keeps appearing. You saw that also 2L plus 2 I was kept writing. So I can now write it in a short form 2 times F instead of writing 2 times L plus 1. So we define a variable F, which is nothing but lag plus 1. Okay, and we choose the lag such that it's sufficiently greater than the system order. In this case, we don't know n. So we assume that we choose a large L that is greater than, such that this L plus 1 is greater than n. Okay, and then we construct the lagged what I call matrix. So for outputs, I've shown how the lag matrix, just as before. You start with yk, and you can go either forward. This might be the, you can go what I call in the forward or backward direction. That depends on whether we write k minus 1, k minus so on. Or you can start with the first variable and then pad it till you actually use f variables totally. Okay, f time instance totally. So that would represent this, what is called the, I still will call it the lag vector, although f is used almost indicating it's a future thing. But let's pretend that this is the lag vector, because if you reverse it, it will be the lag vector, starting from k plus f minus 1 up to yk. Okay, so this is of dimension, of course, because m is the number of output variables. Mf will be the size of this vector. Okay, and now if you do this with u, same thing you do. Start with uk plus 1 and so on, and uk plus f minus 1. You do this with the process noise. You do this with the measurement noise. You do this with the measurement noise for the input and for the output. And finally, you can show that this equation, okay, this state space equation that you have here, okay, all of this, right? You can combine this and write it in one compact form called the subspace-based representation of the system, where the yf, the stacked vector, is written in terms of the state at time k, multiplied by this, what is called the extended observability matrix, gamma f, And then there is another matrix HF, which relates the YF to the input, lag vector of inputs, and also the noise terms will be there. HF multiplying the measurement noise. I'm assuming, no, this is a measurement noise for the output, and this is the measurement noise for the input, and this is what the matrix for the process noise. So all of these three terms that are appearing in equation 2, the last three terms, correspond to the noise terms. The left-hand side corresponds to the input outputs. This is the state, unknown state, and at time k, and this is the lag vector of inputs. Remember, these are the measured inputs. So we know YF and we know UF, but we don't know this matrices gamma F, HF, and so on. We'll define what gamma F, HF is. So when we convert the state space form for this, we'll correspondingly we can also identify what is gamma F, HF, and so on, and GF. Okay, so it turns out gamma F, if you just expand, you will see that this is nothing but this observability matrix, or what is called the extended observability matrix. Those of you who are familiar with state space modeling will realize that, you know, this is your, if you choose a sufficiently large F, this rank of this matrix will be n. Okay, it will be full column rank and cannot exceed that. And this is exactly what identical thing that we are getting here. This gamma F consists of both the measurement matrix C and the state transition matrix A. Okay, and whereas HF incorporates D, C, and B, the direct feedback, the direct thing of U on influence of U on Y, and also the influence of U on the state vector, which is defined by B, and so on. And A also plays a role. So this is the what I call the matrices gamma F, HF, and GF also turns out to be like this, where if there is no process noise, GF will come out to be like this. And if there's process noise, GF actually turns out to be this. Okay. So all of this basically means that we have reconverted the system representation for a lagged vector YF in terms of the lag vector UF and the unknown state variable X of K. Okay. For any time instant K. Now, it is possible now to look at this and say, okay, fine, I can probably take the HF UF to the left-hand side and rewrite this in terms of the unknown X of K and the noise terms. And that's what we will do next. So after next manipulation is we take the UF to the left-hand side here. This HF UF onto the left-hand side. And then we'll get I minus H times YF UF, which is basically I minus HF ZF, where ZF is the stack vector of Y and U. Okay, so don't worry about this matrix. This is only what I call putting all the samples for the lag vectors in one big matrix. So you can work with a single vector for the purpose of theoretical development. But when we do the analysis, obviously we'll work with this entire matrix. So this matrix is nothing but the lagged data matrix constructed corresponding to the definition of YFK and UFK. Okay, so you put these matrix, pack them up and call it ZF at every K, and then put down all the samples into one big matrix. That's what ZF is. ZF is your lagged data matrix on which you're going to operate. So all these symbols now are very, very similar to what we have done before. So the size of this ZF, if you look very carefully, it will be L plus M, which will be the number of variables, into F, because that's your stacking length plus 1, lag plus 1. That will be the total number of rows. And the columns will be number of samples. I have said N, but actually it will be N minus some amount you lose because of your lag. Okay. So for the this will not be exactly, if N is your total number of measurement you started off with, it will be a slight reduction because of your lag. It will be N minus F or something like that, or N minus F plus 1. Okay. So although I've just written as N just to know the sample size, well, that's not critical. Okay. So now in terms of the Z, you can see that once you have taken your HFUF to the left-hand side, you can write it compactly in this form. Some matrix times ZF is equal to gamma of XF plus EF, where XF is defined exactly the same way XK and stacked up to XK plus F minus 1. Okay, and this EF is nothing but the composite noise term. Now, if noise is absent, this will go to 0. This EF will go to 0. And then you can also notice that gamma F is a very large matrix. I mean, in terms of number of rows, it is M times L plus M times F. No, it is M times F. Sorry, M times F. Okay, with n columns, small n number of columns, right? That's what we have said. You look at gamma F. If you look at the columns of C, I should have written MF cross n, where small n, where n is the number of columns of C, okay, or columns of A, if you will. So this matrix is a very tall matrix, if you will, of size MF and cross n. And the rank of this matrix we know is going to be n, that we know for sure thing, because we are from theory, we know that it cannot exceed n if there's no noise. And therefore, you'll see that you can construct what's called a orthogonal projection to get rid of this, of size MF minus n. So you can construct something called a gamma F perpendicular, which is orthogonal to gamma F. Because we don't know XF, we want to get rid of this. The way to get rid of this is to pre-multiply gamma F, which is orthogonal complement, which we have written as gamma F perpendicular. Okay, transpose we have written because this basically matrix will be obtained by transposing it first, finding the null space, and so on and so forth. And that basically is the matrix. So you can look at this matrix gamma F perpendicular transpose, which if we pre-multiply gamma F with that, will make it 0. Okay, the size of this matrix, or the number of rows of this matrix, will be MF minus n, the number of rows of gamma F minus the rank of gamma F, which is basically small n. So this matrix gamma F perpendicular will be MF minus n. So if you multiply both sides by this, you will actually end up getting 0, provided there is no noise. If there is noise, there will be something, right? So what we are interested is, in the non-noisy case, all our ZF will become Z star, and we have got our constraint form that we are looking for. So this whole matrix gamma F perpendicular into I minus HF, not I minus HF, I partition matrix. I is the first part, minus HF is the second part here. This whole matrix, I can call it A. Notice that A can be obtained, this constraint matrix can be obtained, if you give me a set of measurements for ZF by applying IPC or DIPCA for that matter. Okay. So essentially what we are saying is, it is possible to obtain this A, provided we get measurements of this, and we know its measurement error covariance, all that we can also obtain. So let's do the simple case when PF is absent and we have only WF and VF, okay, which is the input and output noise, and then see how we go through this whole thing. And afterwards, we can extend it to the case when process noise is also present. Okay. So these are some observations. When we finally convert it to what we call the subspace representation, the model, we will find that there are D constraints in equation 7, and the D is nothing but, I'm sorry, here it should not be L plus M, it should be just MF minus N. Okay, I'm sorry about that. It should be just MF minus N. So I'll correct it. So number of rows of gamma F minus the rank of gamma F, that will be the size of number of constraints, or the number of constraints in the thing. So since we know F, that's what we are using, our lag. We know M, the number of output variables. Therefore, if we know the number of constraints, which is this quantity, I can obtain N from the number of constraints. So DIPCA gives you the number of constraints, remember, and from the number of constraints, because I know all the other parameters, I can actually obtain N. That's what we are stating here. Okay, so N can be obtained by applying DIPCA on the lag data, and I will be able to use this particular relationship to obtain things. It's just very similar to what we have done before, where the D and the system order are related through the measurements. There were only 2 measurements, one input and one output, and therefore you are able to actually directly define D as L minus eta plus 1, right? That's what we actually got. Here it is MF minus N. F already contains the 1, L plus 1. Because there are multiple inputs, multiple outputs, so that L plus 1 gets multiplied by M, and minus N, that will be the total number of constraints. So D can be obtained from that. So I'm sorry, once you obtain D, you can obtain N. That's the whole idea. So clearly, therefore, the system order can be estimated from the earlier procedure. Okay. But that doesn't solve the problem. What we get is this whole mess, okay, which is called the constraint matrix. So if you look at the first part, that will give me gamma F perpendicular. So gamma F perpendicular transpose, what we call the first part, can be obtained from the first n columns of this constraint matrix. So once I get the constraint matrix, the first n columns will be used to get this gamma F perpendicular, and we can get gamma F perpendicular transpose. Once we get that, we can always get gamma F from there. Okay. Then again by doing a null space of this thing. So gamma F can be obtained. When gamma F can be obtained from the constraint matrix, C and CA and so on, A can be obtained from this, because C can be obtained from the first part, A can be obtained by some kind of least squares. These are all being done already. In subspace ID, this is the same thing that they do. The aim is to estimate gamma F and HF. Once you get them, you can use these two relationships in order to get CA and DB. Okay. So that part of it I'm going to skip, because there's only a set of least squares problem that you have to solve in order to get that. The main thing is how do I get gamma F and how do I get HF? And that can be obtained from the constraint matrix, provided you know what is the number of state variables, size of the or the order of the system. Since we know the order of the system and the constraint matrix can be obtained from DIPCA, therefore C and A can also be extracted. And from the remaining columns, HF can be extracted, from which B and D can be extracted. And these two parts are all earlier done already in subspace-based ID. So we are just going to reuse them. If we have time, I'll just go over the technique for doing that. So let me stop here, because now I'll go to questions. Now I'll go to examples. So before we go to examples, I just thought I'll just take some questions to clarify anything that you may have.
Yeah, may I ask a
question? Sure.
So it seems reasonable that one should only be able to recover a minimal realization. So was there an assumption of minimality in the beginning?
Yes. Yeah, we are directly assuming that you have state space representation is minimal. And what we mean by minimal is if you hit the number of constraints correctly, you'll get the minimum realization, right?
Okay, right. And the other question is, did you say that we need to know the number of states beforehand?
Number of states, N.
Yeah.
No, we don't need to know, because we are saying that N is related to your stacking and number of constraints that you will get. Okay, so forget about this L. It is MF minus N. Okay. Sorry, I just went from full screen mode. Okay. So it is MF minus N. So M is the number of output variables. F is your stacking length plus 1. Now N I don't know, but MF minus N I know, because that's a number of constraints, and that number of constraints are obtained by eigenvalue analysis, right, in DIPCA.
Okay.
So every time we are doing the same thing, we are hitting the number of constraints and then backing out our either the process order in the CISO case or the system order in the multivariate MIMO case.
Okay. Sure. So here, how is HF estimated? You can see.
Okay. So HF is obtained first gamma F is obtained, gamma F perpendicular transpose, right?
Right.
That is obtained from the first n columns of this A matrix. Okay. This A full matrix is called A.
Yeah.
I can put gamma F perpendicular transpose inside. So the first term will be gamma F perpendicular transpose, and the next term will be gamma F perpendicular transpose HF. So the first n columns will give you this gamma F perpendicular transpose. The next remaining columns will give you this gamma F perpendicular transpose HF. So once I know this, right, I can always get HF, and from HF I can get B and D.
Okay, got it. Thanks.
So that's a sequence of steps. First, we'll work with gamma F, get C and A, and then we will use this. We will see the pattern of this. Okay, and then we will obtain B and D from them. But that's just rest of it is algebra, really.
Yeah. So what you get from here, let's say gamma F perpendicular transpose HF, will it have all the block zeros in the right place?
No, it won't, because it's a linear combination. Remember?
Yeah. No, that. Yeah. So Shankar, if I can comment. So the point is you can identify state space models uniquely only up to a similarity transformation.
Yeah, that's what I was about to say.
Because they themselves are not unique, there is no control on the state space basis in which you are identifying. And that's the same even in subspace identification. So we are not solving a constrained state space ID problem. We are solving so-called unconstrained state space identification problem, or in the subspace ID language, this is called freely parameterized state space ID. So we don't assume any structure on A, B, C, D, and so on. So you will obtain gamma F in some other space.
Yeah.
So
pretty much
AC,
like in DIPCA.
So this AC matrices that we'll get will be unique only up to similarity transformation.
Yes, absolutely. That you cannot do anything about it.
Yeah.
Okay, but the point is, you will get the number of states or the order of the system accurately.
Okay.
That is guaranteed.
Okay.
Which means that you will identify a state space model, but in an optimal way.
Right. But the block toplets matrix from any realization, it would still have the same structure, no? HF.
But gamma F, for example, so because HF goes away, so what happens is when you multiply with gamma F orthogonal, no? See, Shankar, can you go to the next slide where you have written everything in terms of this equation 7. So when you look at this equation 7, you will identify only a basis for gamma F orthogonal complement transpose times that I partition minus HF. So you will not get exactly gamma F orthogonal complement transpose. You will get some similarity transformation times that.
Okay, fine.
Even gamma F perp actually is just unique up to the subspace, right?
Yes, correct. Yeah. Yes. So you will not be able to get exactly that. And the goal is also not that. Let me tell you that. We are not keen on identifying a particular state space model. We are just keen on identifying a state space model.
Okay, sure. Thanks.
Okay. I have one more doubt. Maybe I'm mistaken here. But this small f is a number that we are making a choice at the beginning.
Yes, the user specified value. Correct. It is equivalent to lag L in DIPCA.
Without knowing the state space dimension, so I have to start with a pretty large f, is it?
Correct.
Okay. And then do I do any correction on that, or I just
no, you don't have
choice
to.
That
I mean, you don't assume really atrociously high values. Like pretty much like what we spoke about in DIPCA yesterday evening, right? I talked about the effect of stacking lag L. And there also we said the same thing, that the lag L per se doesn't have too much of an impact unless you choose very, very high values. And the guideline for choosing lag L in DIPCA and F, the guideline is the same, more or less. So if you know the process order there, or sorry, not but if you have some feel for it, then you will choose L higher than that. The minimum L that you have to choose in DIPCA is your guessed eta plus 1. But you choose much higher than that because you may be wrong in your eta guess. Likewise here, when you choose F, you will have to choose it sufficiently high. But that's okay. I think what can be done is you can try different values of F and C, whether you get the same N. You will basically.
Right. Are there any questions from the audience?
I just want to add that the lag that you choose, L, the methodology is fairly robust with respect to the choice. You can, for a wide range of L, it works. And so therefore you can cross check again for 2 different values of L. Are you getting the same system order estimate? It usually, I mean, it is a robust method in the thing. And the larger the L you choose, typically the estimates of sigma actually improves. But L cannot be close to the number of samples, obviously. That also, I think, was mentioned by Arun yesterday. You have to choose L much lower than the number of samples, but higher than it can be quite high. You can choose 50 for a 5-order system. It will still work quite well.
And in continuation with what Sanjay was saying about minimality, so here all uncontrollable, unobservable stuff will be completely lost.
Yeah, you will never be able to. In fact, that is a problem with database identification. Doesn't matter which method you choose, no method whatsoever will be able to get you those unobservable, and that is why they are called unobservable.
Yeah.
Okay, or uncontrollable. Uncontrollable because the controllability is a requirement, because you cannot excite those states using those inputs, using the inputs that you have designed. And if those states are not excited, you will not be able to observe them. So that's why both controllability and observability are required for state space ID.
One more thing that usually comes up here is the persistency of the excitation.
Right.
That is taken care of by the stochasticity, I believe, right?
No.
I see.
No. Stochasticity is not going to affect, because the deterministic matrices, your ability to identify them and so on, is governed by the persistency of the input excitation. That is not taken away.
Okay, so that is a standing assumption.
That requirement, yeah, that exists.
Right. Okay.
But the only thing is, we don't need a full band input signal. You just need the input to have frequencies within the bandwidth of the system.
Right.
That anyway, no method can escape that. If you don't ask questions, how can you actually determine if the candidate is suitable for the position? Right?
Yeah.
Unless you're able to read mind, maybe AI-based things will come in, and where you don't excite the system, it will just scan and say, this is the model. Like Google says, no, I can look into the eye and tell you whether you have cancer. So
this assumption never came up in the discussion so far.
Yeah, that's what I thought.
Yeah, but that's correct. We admit that it is not so explicitly there. But what happens is, if the persistency is not satisfied, somewhere the covariance matrices of that particular order will take a beating.
Okay.
That kind of link between persistence of excitation and the identification is kind of explained clearly in the subspace ID literature.
Okay.
I mean, all the other assumptions that you make typically for ID, system identification, actually holds here. We are not overcoming any of those requirements. So the design of U is important in actually getting you the proper. For example, if you apply this to a closed loop system, you will get into problems, because it might be that it's a very tightly controlled and it may not show excitation, or I mean, there's no excitation in a set point. For example, if it's constant, you shouldn't gather data from that particular obviously operating condition. You should gather data when either the set points have been actually changed quite vigorously, or you change your inputs vigor for by doing an open loop test, whichever way. Yeah.
Okay.
Maybe just to follow up on that. So Sanjay, what happens is, ultimately you construct your ZF, and then you will have to do a covariance analysis of the ZF. And the persistence of excitation requirement comes up there. Suppose you give an input, something like a sinusoid, which has only one frequency, then the covariance matrix will be highly rank deficient. You will not be able to estimate the correct order. So that is where it shows up.
All right. Okay, thanks.
Thank you.
Can I go ahead? Okay.
Yes, please.
Yeah. So just for illustrative purposes, we took a 2x2 dynamical process that has been generally used in subspace ID also to illustrate. So here is a description of the state space model for that. And here also the data generation we followed what was already done earlier. So we didn't try to actually modify it in any way. So the input was sum of sinusoids that were defined in this manner for both the input 1 and input 2. And these are A1 and A2 as scaling factors to make the input unit variance. Whatever was defined in the earlier work, we just followed it. Okay. And then we actually generated noise, added it to the true values to get the measured values of Y and U. So this is what we actually did in order to simulate the data. And SNR, the values of sigma V, that is that the variances of both the inputs and both the outputs, V is for outputs, W is for inputs, again to remind you, were chosen so that the SNR was basically around 10 for all the 4 signals, right? So that's exactly what was done. And now we started with some lag. Now in this case, you might say L is very small. You can have chosen from L is equal to 10 or 20 or 50, whatever. And we have done all of that, right? We changed L for a wide range of L. The results are pretty much similar. But I'm just illustrating for L equals 6 for what I call for the sake of this particular lecture. So in this case, if you look at the total number of input plus outputs, there are L is 6, F is 7. So 7 into, there are 2 outputs and 2 inputs. So totally you have about 2 inputs. That's what your 2 outputs. That's what you should worry about. And 2 into 7, 14 minus 1, 13 constraints you can actually assume for the largest number, right? So D can, at best, D can be just 1 less than the total number of lagged output variables, right? So that's what was done. And starting from 13, you just work your way downwards till you hit the right thing when the number of eigenvalues, unity eigenvalues is equal to the D guess that you start with. So we always start with D max. There are several reasons for this, because our hypothesis testing is designed to look for evidence for rejecting the null, right? In this case, the null is 13 eigenvalues are all equal to each other, the last 13 eigenvalues. And if you have evidence to reject it, you will reject it. And then you go to the next one, 12. And if you have evidence to reject it, you will go to the next one, 11, until you don't have evidence to reject it, at which point you stop. Okay. So this is converse of starting with a very small D and then working your way upwards. Yesterday I even discussed this with Arun. So I was saying that usually statistical tests are designed so that the null hypothesis can be rejected. You look for evidence for rejecting the null hypothesis. That's how you should construct the hypothesis, null and alternative, if you have if you have choices. And in this case, that's why we chose this approach. So every time there's evidence, the data provides evidence for rejecting the null, we reject and just go forward. Otherwise, we don't ever say we accept the null. We say we don't have evidence to reject the null. That's the way the language is also written in all statistics books. Okay, so that's one of the reasons that we've done this. Okay, and as we follow, we'll finally end up getting essentially what we should get is eta n is equal to 4, which means we'll end up getting 10, D equals 10 as the correct thing, at which point the null hypothesis is no longer rejected, and we stop that. Unfortunately, I have not shown the results. If I have chance, I'll just bring up the thing, okay? Because this was more recently done. We just submitted the paper in this case. So I just couldn't prepare my slides fully. But we can trace the hypothesis test, and it starts with 13 and stops at 10, at which point we actually say 14 minus 10 is 4, and we get the correct estimate for the system order. Notice that's a 4th order system, right? X is 4, state dimension is 4. Okay. We also get estimates for our error variances, both input and output, as part of DIPCA, and this you will find that the 95% confidence interval again contains the true values for all 4. So the error variance is also estimated fairly decently for this choice of L. Okay, and then we apply we extract gamma F, we actually extract HF, then we actually do all the least squares estimate and so on and so forth, and we get ABCD. And this will of course not correspond to the ABCD of the truth, naturally, because the basis is different, right? So you got some very structured A in this case, and this is completely different, okay? The only way we can compare is perhaps look for whether this and the 2A share the same row space and column space and so on, but those are all cumbersome ways of testing, because you have to test A, B, C, D, and so much. So the one way of checking whether you've got the correct model is to look whether the zeros and the poles of this multivariate system, MIMO zeros and poles are correctly estimated. That's one way of testing it, whether you got the correct system, because those are invariant to the representation, right? So that we can do. And it turns out that we actually look at the pole estimates. They are pretty much bang on target. Okay, all the 4 poles that, there are actually 4. There are, what do I call? I mean, complex poles, and that you find 4 of them and conjugate pairs, and you can actually estimate them fairly accurately using the estimated D, ABCD, and the true ABCD. The true ABCD were put as circles, and stars are basically through the using the estimated ABCD from the model, from the procedure. Okay. On the other hand, the zeros are not estimated that accurately. You can see 2 of the zeros are fairly well estimated. I mean, almost close, very, very close. But 2 of the other poles, zeros are slightly farther away from the truth. However, when we do a Monte Carlo simulation or bootstrapping, we are able to show that they are still unbiased estimates of these, both the real and imaginary part. So that required some little bit of effort to actually say how to compare, but we could compare both the real and the imaginary parts of these poles, and we could find that by and large they were, you could say they were unbiased estimates, provided you chose a sufficiently large n. The number of data points that was required to establish this was close to about close to 5,000 plus data samples, and the lag also had to be chosen for more than 10 in order to actually get what we call unbiased estimates of these particular zeros. All the others were well estimated. That these 2 zeros alone had to be actually, you had to take a larger value of L and a larger value of number of samples to get it. So we compared with earlier SMI methods, what we call instrument variable methods, which have been used for subspace identification, including the EAV case. People have done this. The difference between our approach and what earlier people have done, in the earlier approach, they try to kill the effect of the noise. If you look at this particular equation, in the noisy case, on the right hand side, you will have a gamma F transpose EF, right? So that will be the covariance matrix. So people don't know what EF is, what is the variance of EF, because it contains many parts. It has the variance of the output, the variance of the input, multiplied by HF is also not known, GF is not known, process noise not. So it was quite what I call it. It's not very easy to see how to actually handle this errors in the noisy case. In the noiseless case, of course, we can say there's a constraint, but what if we have noise? In the earlier case, what they try to do is kill the effect of this noise by using what they call instrument variables. And typically what they do is use the past. That's why they use this future notion of F is future and notion of P is past. What they do is divide the data sets in 2 halves. One half is what they call the future one, and the other half is the past data points. The past data points, basically measurements of input and output. In the absence of process noise, you can use both inputs and outputs to actually kill out this noise. You can post multiply this by the ZP that represents the data before F. When you start, let's say F starts at some value K, index K. So before K, the data is used and stacked in the same manner using some lag, maybe the same lag as what you have used for this. And then you construct that matrix and post multiply this, because the errors in the past data are uncorrelated with the errors in the future. Remember, Gaussian white noise is what we assume. And therefore, you can actually, when you take the expectation, this part of it goes out. So most IV methods essentially use the past measurements in order to kill out the effect of noise. And then they work with the ZF ZP transpose, what they call, right? The instrument variable is used to post multiply this, and PCA is therefore applied on this because that has very little noise or practically absent, right? And the advantage of this is you don't have to worry about the noise, whether it's correlated and things like that. Typically, right? Even if it's correlated, you can do by shifting the difference between past and future, sufficiently separating the past and the future. You can get rid of the noise effect, even if it's correlated. But what the difficulty with this is that it doesn't provide you any estimate of the error variances, right? You don't even attempt to do it in IV-based methods. You're only interested in the system matrices A, B, C, D, not interested in estimating this. But this is valuable information I told you. Secondly, there is no idea of how do you obtain the system order, because there is no evidence for that, and then you have to use some heuristic to estimate the system order. So those are the two lacunae, if you will, of the IV methods. The advantage is that it doesn't have to worry about what kind of noise structure it is. Okay, so that's one advantage I think they have, but we have to worry about it. So in our case, what we do is we try to use the error variances to scale the data. So in the absence of PF, you can actually show that all you have to do is scale the thing by the error variances, respective error variances, which can be obtained as part of your DIPCA method. So when process noise is not there, then it's very easy to see what the scaling is. When process noise is there, then you have to reconstruct this GF and include that in your scaling strategy. That's why I didn't do process noise first. So this is just to distinguish between what people have done earlier, what's called the IV method, vis-a-vis what we are doing, where we are trying to estimate the error variances, use that to scale the data. We are not getting rid of the noise. We are including it. We are inclusive, whereas IV methods are exclusive, if you will, right? They exclude the noise by using what they call instrument variables or past data. So that is just to give you a quick overview of what people have done. And when SMI methods are used, the estimate of these zeros are even worse. Our method is much closer, but whereas SMI methods actually are much farther, and they get even biased estimates. So the reason for that is not very clear why SMI methods gives biased estimates. But fortunately for us, if you use a sufficiently large N and L, we were getting unbiased estimates of all the zeros and all the poles for this system. So we have tried, of course, other systems and so on. So here's the final thing of the predicted was the actual output based on the estimated model, and for output 2 also. Okay, so just as a comparison to make sure things are okay, right? So I've just not done the process noise case because we are running out of time. I knew that. So essentially, we got a pipeline now for estimating system matrices and noise covariance matrices using DIPCA and SMI methods, right? Okay, I mean, simulation results strongly enforced is not the correct. Okay, strongly what I call the efficiency of the algorithm is basically indicated by simulation what we have done. So right now it's limited to process noise, but we have done the process noise. The problem is when you have process noise, you don't know the rank of the noise. You don't know whether this is full rank or as the same rank as N or lower rank. So there are ways of getting around it. What you do is you try to use a representation which, because there are multiple representations of the state space system, you choose a representation that you think is convenient. Okay, so just to give you an idea what I mean by that. Suppose, let's assume, okay, this G is identity. For the sake, we will consider P as full rank and G is identity. Okay, so in which case, what you can do is, instead of just working with this state space representation, we assume that we got a new state space representation where the covariance matrix of P is identity. How can we do that? We can scale with the square root of the covariance matrix of the process noise covariance matrix, right? Square root of the process noise covariance matrix, if we multiply and use that as T, then we get a new state space representation where the new process noise will actually have an identity covariance matrix. That gets rid of the parameter of the noise covariance estimation of P and allows us to basically work with what I call an extended version of what we have done here. Okay, that's one way out of it. There's another way that is we have not tried as yet, which is called the innovations form of the state space representation. That also gets rid of this P, essentially by parameterizing this process noise as a output noise. So this V appears here in both as process noise and measurement noise. That's called the innovations representation. And we haven't tried it as yet, but I think that also could be tried in order to deal with process noise in general, even if it's not a full rank. So those issues are still to be cleaned out, but the procedure is available right now, also for estimating let's say for dealing with process noise. So I will stop with that, and I ask, take again any additional questions you might have. I'll just basically, okay. So here basically you have the how what you call the A matrix and C matrix are extracted from gamma F and so on. So how D and B are estimated from HF. So this is just for completion, but those procedures are well known, certainly well known. This is not we didn't develop it; they were already available for us. So, any questions regarding the process procedure itself, or any questions regarding the overall set of lectures?
May I?
Yeah, sure.
Yeah, I had promised to ask some questions yesterday.
Yes.
So,
Please.
yeah, some of them got answered along the way. But so yesterday you did. So this pertains to the lecture yesterday evening about DPCA. So you showed confidence estimates, or rather confidence intervals.
Is it DPCA or DIPCA?
Well, okay. Yesterday evening was which one?
Our method is DIPCA. DPCA exists in literature, but it's quite restricted in its applicability.
Okay. Then it is DIPCA. I'm sorry.
Yeah, please. Yeah.
So you showed confidence intervals yesterday. So how do you obtain confidence intervals? Is there my understanding, limited understanding, is that you need some distribution.
Correct. Right.
Yeah.
Right. So what we do is, of course, deriving analytical expressions for the distributions of estimates is very difficult. We don't know if we'll be able to do it in our lifetime. So what we do is we follow the bootstrapping method. So we generate bootstraps from the data. In that is, what we do is, suppose you have 5,000 data points, just for the sake of discussion. Then we consider smaller subsets of data. So if I have 5,000, I can pick many different subsets and construct my data matrix. What I mean by subset, of course, a subset has to have a continuity in time. I can do that. And for each such data set, I can estimate the coefficients. Okay, so we don't do bootstrapping in that real sense. We just build our model on subsets of data, smaller subsets of data, and then we estimate the coefficients. And then we don't even have to fit a distribution. We can get the quantiles, and from the quantiles we can get the probability intervals for the estimates. From the probability intervals, we estimate the confidence intervals.
Okay, right. So when you say a subset of data, each subset would be a collection of input-output trajectories, right?
Correct.
Okay, all right. Okay, that was helpful. Then the other question is there an online version of DIPCA?
Good question. So
data keeps coming and you keep, data keeps coming and you keep updating your model or something.
Correct. So we have a master student who is currently working on first developing a recursive version of IPCA for the steady state case. Because there is no recursive version, even a very well accepted recursive version of PCA also is not available. Yes, there are maybe 2 or 3 methods in the literature that attempt to do recursive SVD. We are currently examining those. Once we have kind of narrowed down or converged to a recursive version of PCA, then going to IPCA will be the next stage, because there is an iteration that is involved. So currently we are developing a recursive version of the IPCA, which is for steady state case. Once we are successful, hopefully we'll then be able to develop a recursive version for the dynamic case.
Okay. So if you get it, just drop me an email. I would be very interested to see it.
Yes, certainly.
Okay, thanks.
Yeah, thank you. Very nice pointed questions.
I just want to add one thing. You said that different trajectories of Y and U. So what we do is, if you have done one particular simulation, let's say, or one particular realization through experiments you've got. So then if you have, say, you've got 5,000 let's say samples, then we construct the lagged matrix for any given lag. And then once you've constructed the lagged matrix, you can choose a subset of the columns for doing your IPCA. So let's say you take 70% of the columns of the lagged matrix, apply PCA or IPCA, and you got one estimate. Take another random sample of 70% of these columns, you will get another estimate. Remember, once you have lagged it, you don't have to worry about the ordering of the columns, nothing, right? Because the contiguity is maintained within each of the lagged vector, and that's all you need. Okay.
Yeah.
That's the beauty of this. I mean, in PCA, you don't care how the samples are ordered, really. So once you've gone to that stage, when you're constructed the lagged matrix, you can take a subset of these, and corresponding to every subset that you choose, you can get an estimate. And from that estimate, I mean, if you do a sufficiently large number of trials, you can actually get a 95% confidence interval, assuming that the estimates themselves are normally distributed, right? Or a t-distribution if you are so particular.
Yeah, so as long as the columns are related to each other, there is a continuity in the columns respecting constraints. You don't have to worry about the continuity of the rows or the regularity of the time instance.
Yeah. Sorry,
that's
rows,
what Shankar is pointing.
Not rows, not columns, rows. I keep working with the other way around, you know.
Yeah, correct.
So thanks. Yeah, the rows are the samples. Sorry. Yeah.
Yeah. Once you make sure that you have chosen your lagged data vector properly, then you don't have to worry about the regularity of the observations. I mean, I could pick, for example, randomly any samples from 1 to 5,000 of sufficiently large size. And that could be even 4,000, right? And I can construct many such data sets. So basically it's all about picking 5,000, 5,000 C, 4,000. There are many such combinations. So bootstrapping is a very easy there. And that's what we do in our GUI. So when I will also share the GUI, Sanjay, so then you can play around with it and let me know.
Oh, okay.
That provides, so the GUI does this bootstrapping and provides the confidence intervals.
I'm tempted to ask one more question.
Please.
Although I think I have delivered on my promise already. So,
but you said there are no constraints, so you can go ahead.
Well, no constraints for me and perhaps for you, but the other participants too.
Yeah.
So, okay, last one, I promise. So where would things break down if the noise was not Gaussian? How much of this we can keep doing? Till what point we can continue doing this and then go no further if we know it's not Gaussian?
I don't know. I think the non-Gaussianity perhaps will not affect the order, will affect the efficiency, like in least squares. No? So in the least squares, if you go back to the OLS case, the non-Gaussianity is not such a binding criterion on the bias. It is only a criterion on the efficiency of the estimate. So the most efficient estimates, the minimum variance unbiased estimator is the least squares is that, provided you have Gaussian white noise affecting. So if you deviate from Gaussianity, the minimum variance is the one that is that takes a beating. So I suspect here also non-Gaussianity would affect the precision of the estimates, not as much as the accuracy. But we have not done any simulations. I mean, this is what my understanding is just by.
Yeah, but there is one more aspect. We do exploit Gaussianity when we set up the MLE for estimating error variances.
Yeah, but if you do a least squares there, then you don't have.
Yeah, then we don't have to worry. So we have right now used MLE. Then we have to shift to a least squares kind of approach in order to estimate the error variances. Okay, so get rid of this exploiting the likelihood function, which we can construct.
But that is where I think we will run into efficiency issues. That means our error variances may not be estimated precisely. The errors on the error covariance estimates can can become large then compared to the Gaussian case. But otherwise, I don't think the order and so on is affected.
Okay, thanks.
Are there any more questions from the audience? You know that you can just unmute yourself and ask your questions. So while people are thinking of questions, let me take this opportunity to express our interest also in this area, in this topic. So we will also be, I think I can speak for our group here, Control and Computing Group in EE Department, IIT Bombay, that we will also be very much interested in that recursive SVD, if you can come up with that. And yeah.
Sure, yeah. Certainly, we feel that it's a very important and relevant method to develop for online applications.
Yes.
We'll certainly be happy to collaborate.
Yes, certainly. For that matter, we actually in our group, we have a master's degree course called Matrix Computations, where we do teach singular value decomposition. We start with the Gaussian elimination, the numerical, basically numerical linear algebra course. So we teach QR decomposition and then eigenvalue computations and singular value decomposition as well.
Very nice. Yeah, those. Unfortunately, in the wave and in the winds of deep learning, people think that there is no point in learning any of this. But I just tell my students that please, machines have begun to learn. Then you should not be lagging behind.
Nice one. Yeah.
Right. And unfortunately, today machines are learning, and we are focusing on earning. So. In fact, I wanted to ask among the audience, how many of them are actually familiar with PCA? At least, if I can have a show of hands, that would be nice. At least people would have learned PCA or not. We'll be happy to know. At least that, I think, is an easy question to answer. So how many among the participants right now, if you can just even have a show of hands, or you can unmute yourself and say that, yes, you are familiar with PCA earlier. We didn't have any chance to ask any questions prior to the workshop.
You can either raise your virtual hand or you can just say, unmute yourself and speak up.
I don't see a virtual hand.
No, there is a smiley, no? Sanjay, there is a smiley.
Smiley, yeah.
So there, if you click, so now it's not just raise hand, you can sort of clap, you can send like reactions.
Yeah. At least they can type in the chat window. Yes.
Yeah, there is a chat I can see.
Amol
Patil. Yes.
It's a dimensionality reduction technique. Yes.
Yes.
Yeah, that is how PCA is familiar to everyone. Always as a dimensionality reduction technique. It's amazing how actually the original paper to which PCA is credited, which is Pearson's paper on the fitting of lines, the original problem actually did not become very popular when it comes to PCA. So the dimensionality reduction application is the one that made PCA very popular.
Perhaps if I say that Netflix's movie recommendation problem also was solved using some form of PCA, people will relate more.
Interesting.
Yeah, Netflix had this prize for overcoming their movie recommendation system. So many groups participated. Finally, the group that won the prize that used a form of collaborative filtering, which uses SVD.
I see.
Yeah.
Interesting. And we also wanted to know how many of the participants, how many among the participants are faculty members versus students or research scholars or postdocs.
So perhaps it wouldn't be a bad idea if we request the participants to unmute themselves one by one and just give a brief.
Yeah, it'd be nice, no? So we can start alphabetically with Amol Patil. Would you be able to unmute yourself and tell us? Yes, Samol, you're unmuted, but we can't hear you. Maybe they can type in the chat. What about Aniruddha Roy?
Amol Patil says mic problem.
Yeah, okay. What about Atul Sharma?
Yes, sir.
So we just wanted to know whether you're faculty, research scholar. Did you manage to attend all the sessions?
Yeah.
No, did you manage to attend all the tutorial sessions?
I have tried to attend all the sessions. Actually, I was
Okay.
little
Can
bit
you tell
interested in
from where you are? Where do you?
I'm currently a PhD student at IIT Delhi.
Oh, I see. Okay.
Yeah.
In which department?
Electrical department in control and automation.
Okay. So do you work with Hari Prasad or?
No, I'm working with the Professor Janardhan.
Janardhan. Okay. Thank you.
Thank you.
How about Arnab? Arnab Pal. Komal Agarwal.
Yes, sir.
Yeah, just please can you introduce yourself and tell us if you attended all the sessions and did you find this beneficial?
Yes, sir. So I am a research scholar in IIT Palakkad, and
Oh, I see.
I joined in August, this August only.
Which department?
Electrical engineering.
Okay.
Yes, sir.
Did you manage to attend all the sessions?
Almost yes, I attended, and the sessions were very good. Yeah, I really enjoyed.
Okay, so I hope I'm sure some of the things must have gone above the head.
Yes, sir.
Yes.
I was also like yesterday only. I think we got the link that we can again watch some of the sessions. So it's very good that we can see them again.
Yes, absolutely.
Yeah.
I think it's important to ruminate.
Somehow get the link to those.
Sure. Yeah, we hope, and do feel free to send us questions, right? Even as you are listening to this after the conference.
Yes, sir. Yes.
Yeah, thank you.
Okay.
Imrul?
Yes, sir. Am I audible?
Yes, sir.
So my name is Imrul Kais. I am a research scholar in E Department Control and Computing Group, IIT Bombay.
Oh, nice.
So in fact, I am working with Professor Devasattam Pal.
Oh, okay. Nice. Okay. So did you manage to attend all sessions or only those sessions where your advisor was able to attend?
I attended the plenaries and few tutorials and some of the regular sessions.
Okay. So yeah, hopefully you found these talks useful.
Yeah, certainly.
Yeah, they also had the job of student volunteers for this whole conference.
Yeah.
We are actually grateful to their
that's a rewarding experience.
Humongous effort. Yeah. Yes.
They offer a lot of help, and in turn, I think it's also rewarding to them.
Yes.
Thank you, Imrul. Manas?
Yeah, thanks for the nice presentation.
Yeah, thank you. Manas, would you be able to unmute? Okay. How about Mohan Kumar? Nipen Kitsaria. What about Nirlipta? Okay, so it looks like Nirlipta is unable to unmute. Pantula Devi, Priyanka? Would be able to introduce yourself. Rodrigo? Okay. Sri Kirti? Yeah.
Hello, sir.
Yeah. Yes, Manas. Yes.
Actually, I was having a problem with network, so that's why I got you.
Sure, please. Yeah. So,
Okay,
where are you from?
I am from Pune. I was from Department of Instrumentation and Control Engineering from COEP.
Oh, nice. Okay.
So I have completed my graduation in August 21, and currently I'm working as a software engineer.
I see. Okay. So did you find any of the sessions useful to you?
Yes. I was mostly focused on the control systems, which was taught for us in the college. I found it, so I found more detailed version of what we had been taught.
Very good. Very good. Thank you. Thank you, Manas. Sri Kirti? What about Srikant? Srikant Kavirayani?
Sir, good evening. I'm Dr. Srikant from Gayatri Vidya Parishad, Visakhapatnam. I have attended almost most of the ICC control conferences. And
nice.
This year also I'm attending. My research area is controls. So I would like to know some of the latest trends and what is happening.
So are you a faculty member?
I'm a faculty member, sir.
Okay. In which department?
Electrical engineering.
Okay. So did you manage to attend all the sessions of this tutorial talk? All the 6
Yeah,
sessions?
most of them. When it is virtual, we have a problem that we still have to take up the classes work and
I
all.
know. Correct.
So
People expect you to be essentially at multiple places at the same time.
If we are away from the college, it is a different story. But when we are on campus, it is taken in a different way. So
True.
I had to miss some sessions.
So I think this period teaches us that when we are at work, we should be doing work, and when we are at home, we should be doing it. We should not wish for an interchange of venues.
Yes, true.
Yeah.
Thank you. For,
Vijay Kumar Reddy. Okay, we don't have any response. Did we have Alvin? Alvin, I think, just joined back. Alvin, would you like to unmute yourself and introduce?
Yes, sir. Yeah, actually, I felt little interested in this PCA. Actually, I work in controls in IIT Palakkad.
Oh, I see. Okay.
Yeah.
So, which department? Electrical engineering, is it?
Yeah, electrical engineering. I'm doing MS there in. Yeah.
Nice. So hopefully you found some of the talks useful
it's a
to
new
you.
Topic. Still, yes. It was interesting actually. So I will try to go through the recording also, so that maybe it will be useful.
Sure.
Yeah.
Thank you. Thank you all. So I think I think we are done.
Thank you so much.
Thank you, Alvin.
Yeah. Right. So perhaps we can close this session, but before we close it, I would like to take this opportunity to wholeheartedly thank Professor Narasimhan and Professor Tangirala for this truly enlightening series of lectures on a fascinating subject. No word of thanks is sufficient to express our gratitude to you, and
we are grateful.
hope that we'll have more opportunities to listen to you in future, possibly in person. Yeah.
Sure. Yeah, we also wished that this was in person, and then it would have been a single day affair.
Yeah, right.
Yeah.
Sanjay, would you like to add something?
No, I think you summed it up quite well. Thank you, Professor Tangirala and Professor Narasimhan.
Yeah, thanks to ICC. Thanks to all of you.
Yes, also thanks to all the participants.
So good.
Great coordination.
Thanks for giving us the opportunity to talk to you guys.
No, really. We had planned a workshop like this in an IFAC conference before last year, but then we had to withdraw because of all this changeover to virtual and so on. And then we said, okay, ICC is an equally good venue for sure to reach out to the control community. And of course, we have been, I have been attending ICC almost every edition. In fact, the first edition of ICC took place at IIT Madras.
Yes, right. I attended that one.
Yeah, and I had a
January,
short tutorial talk there as well on time frequency analysis and wavelet transforms. So it was a great homecoming for us in terms of tutorial talks. It was good. Very nice. Yeah. So we look forward to meeting all the participants and all you folks in person at some point in time very soon. Thank you very much.
Yes. Thank you. So with your permission, I'm going to, yes, Professor Narasimha.
No. Good evening to all of you. Thanks again for giving us this opportunity. Yes.
Yes, and we really look forward to meet you in person sometime in future.
Absolutely,
Yes.
Absolutely. Thank you very much. Bye.
So with your permission, then I'm going to end this session.
Sure. Thank you. Yeah. Good evening.
Thank you.
Yeah.
Good evening. Bye-bye. Take care.
Bye.